In this video, we're going to focus on this series given by the sum from 0 to infinity of arctangent of n over 1 plus n squared. We want to use the integral test to study its nature. That means to see whether it's convergent or divergent. The first thing that we need to see is that we can let an, the general term of this sequence, is arctangent n over 1 plus n squared. So when n is 0, we have 0. Okay? So starting from 0 or 1 doesn't matter, because a finite number of sum won't affect the convergence of the series. Okay? So our aim now is to see that it's positive, because we remember that arctangent is like this. Okay, so we are in this part. Okay, this is pi over 2. So it's always positive divided by a positive number, so that means an is positive. The issue that we're going to face is that we need to prove that an is bigger than an plus 1. That means our series is decreasing. Okay, so to do that, we have to apply the mean value theorem. But there is another way. We can consider the function f of x as arctangent of x over 1 plus x squared. Okay, so if we compute the derivative for this one, we get 1 minus 2x arctangent of x over 1 plus x squared. So we see except when x is 0. Okay, if x is 0, we get 1. But if x is different from 0, this one is always less than 0. That means our series is decreasing. Okay, that means this is always true. Okay, except when n is 0. Okay, because when n is 0, we get 1, which is not less than 0. Okay, so we omit that, because here when n is 0, we're going to have 0. So it's always decreasing. Let's start from 1. Okay, so we have this one fixed by using the derivatives. The next thing that we need to see is that if we let an is fn with f a function that we let it equal to this one, so we need to check our conditions for the integral test. So f is positive. Okay, this is positive. Decreasing. Okay, it's decreasing here, and it's continuous, on this interval. So 0 plus infinity. Okay, or 1 plus infinity. So the integral test tells us that the nature of this integral, improper integral, is the same as that of this series. So if this one is convergent, this series is convergent. If it's divergent, this one is divergent. So let's use this one. Okay, so we have 0 plus infinity of arctangent x over 1 plus x squared dx. So here we can use change of variable. So if we let y is arctangent of x, then dy is 1 over 1 plus x squared dx. So when x is 0, when x is 0, y is 0. When x is in infinity, y is pi over 2. Okay, so we have y dy, because dx over 1 plus x squared is just dy. Okay, and here we know this one. We know it's 1/2 y squared between 0 and pi over 2. Okay, this gives us pi squared over 8. Okay, and therefore this is finite. That means this one is convergent. Okay, that means our series is convergent. That means this series is convergent according to the integral test for series. Okay, here we started from 0, we could have started from 1. So if we start from 1, we're gonna get 1 by, okay, pi over 2, but let me see, 1, oh, pi over 4, here, pi over 4. So 1, 1x is 1, y is the arctangent of 1, which is pi over 4. That means y dy equals y squared over 2, which is giving us 1/2 pi squared over 4 minus pi squared over 16, and this will give us 1/2 3 pi squared over 16, which is giving us 3 pi squared over 32. Okay, and it's the same. Okay, it's convergent too. So if we do it, if we start from 1, okay, because we want to avoid this here, the series is decreasing, because if it's between 0 and 1 here, between 0 and 1, it's increasing. So an is less than n plus 1. But once we are here, okay, it's always decreasing. So that's why we get rid of this one. But anyways, it's not gonna affect the convergence of the series because it's only a finite number. But you see it here by your eyes. You see that we always get it convergent. Okay, so this shows that the integral test for this one is helpful without going any further. So this means that we proved that this series is convergent. Thank you.